Picture this. It's late on a Friday.
Oh, the classic setup.
Right. You are a developer trying to push out one last update before the weekend. You're rushing, you're tired, and, well, without thinking, you accidentally hard-code your production database password directly into a container image.
Ouch.
Yeah. You build it, you push it to a public registry, and you go home. And then you wake up on Saturday morning to a panic-inducing email from your security team and a $50,000 cloud provider bill.
Because the bots found it.
Exactly. Automated bots scraped that registry, found your password, and just used your infrastructure to mine cryptocurrency all night.
It is quite literally the absolute definition of a developer's worst nightmare. And, it is incredibly common because managing sensitive configuration in a distributed environment, it really feels like trying to secure a moving train.
Okay, so let's unpack this. Today's mission is to make sure you never find yourself in that scenario. We are doing a deep dive into mastering the Kubernetes environment. Now, we're assuming you already know the basic building blocks, right?
Right, like what pods, deployments, and services are.
Exactly. But knowing how those objects function in isolation versus knowing how to orchestrate them securely at scale, I mean, those are two entirely different skill sets.
Oh, completely.
Yeah.
Mastering the environment is where the real engineering happens. It's the difference between an application that just, runs and an application that is resilient, secure, and portable.
Yeah.
If you are preparing for the Kubernetes and Cloud Native Associate exam, the KCNA, or, frankly, if you're just trying to survive your next production deployment, you have to understand the underlying mechanisms. You have to know how Kubernetes organizes and configures its workloads.
So to fix our developers' Friday night disaster, we first need to understand how the system manages just the sheer volume of resources running inside it. Because if you dump hundreds of microservices into a cluster without any structural hierarchy,
you get absolute operational chaos.
Right. So let's visualize a Kubernetes cluster as this massive corporate office building. In this architecture, namespaces act as the different floors of that building. You put, like, the front-end team on floor 2, the back-end team on floor 3.
It gives you that really necessary multi-tenant structure. The immediate utility is organizational separation, sure, but the real operational power of namespaces lies in resource quota enforcement.
Oh, okay.
Yeah, it's the solution to the classic noisy neighbor problem.
Right, because if I just let my analytics team run huge data crunching pods on their floor without any limits, they could theoretically consume all the CPU and memory in the entire building, right? Just starving the production web servers on the floor below them.
Which, honestly, happens constantly in poorly configured clusters. But by implementing a resource quota object at the namespace level, you establish a hard limit on compute consumption for that specific floor.
So you just cap them.
Exactly. You dictate that, say, the analytics floor can only draw a maximum of 20% of the building's total power. If their workloads spike and try to draw 21%, the API server simply denies the request to spin up new pods.
Wow.
Yeah, and the rest of the building's infrastructure remains entirely unaffected.
That structural isolation is so crucial. But when you spin up a brand new Kubernetes cluster, the building doesn't come completely empty, does it? There are 4 default floors already constructed by the system.
Right, the system defaults.
Yeah, default, kube-system, kube-public, and kube-node lease. Now, I know the default namespace is basically just the lobby. If you don't specify a floor, that's where your workloads get dumped.
Yeah, the dumping ground.
Right. But kube-node lease, that sounds a lot more mechanical. What is actually happening on that floor?
So that floor manages the literal heartbeat of your cluster infrastructure. Yeah. Every single physical or virtual machine, every node in your cluster, has a lease object inside the kube-node lease namespace. Under the hood, the kubelet running on each node sends a pulse to that lease object, usually like every 10 seconds, just updating its timestamp.
Wait, so it's basically the node shouting, hey, I'm still alive, keep giving me work.
Precisely. It's a literal heartbeat. If the cluster control plane notices that 40 seconds have gone by without a heartbeat update on that lease object, it assumes the node has critically failed.
Oh, wow.
Yeah, and then the system automatically triggers an eviction process, rescheduling all the pods from that dead node onto healthy ones. It's a really fundamental mechanism for self-healing.
That's a brilliant way to handle infrastructure failure. Okay, then there's kube-public, which is historically readable by all users, even unauthenticated ones. And finally, the big one, kube-system. Now, if I'm a developer just trying to deploy my app, I should never touch kube-system, right?
You avoid it entirely, like the plague.
Good to know.
If the cluster is our office building, kube-system is the mechanical room in the basement. It houses the essential control plane components. So the internal DNS servers like core DNS, the networking controllers, the kube proxy rules. Modifying resources down there without knowing exactly what you're doing is the fastest way to cause a total cluster outage.
So we stay out of the basement. Got it. But here's where the floor metaphor gets a little complicated.
Yeah.
If I have a front-end application on floor 4 that needs to pull data from a back-end database on floor 5, how do they actually communicate? Because they have to cross that boundary.
Right, and this is handled by services, which provide stable network endpoints for your pods. But services are namespace scoped. They belong to their specific floor.
Right.
So to bridge the gap, Kubernetes utilizes its internal DNS routing system using a fully qualified domain name, or FQDN.
Right. The syntax for that is service.namespace.svc.cluster.local. So if I'm on the front-end floor, my application code doesn't just ask for the database. It has to explicitly address the request to the database service located in the back-end namespace.
Exactly. But what's fascinating here is the underlying architectural philosophy that governed that design choice. And this brings us to a massive trap that catches both KCNA exam takers and seasoned engineers.
Okay, what is it?
By default, Kubernetes implements a completely flat networking model. Any pod can communicate with any other pod across any namespace without restriction.
Wait, hold on. Seriously. So if my staging environment is compromised on floor 3, those attackers can just route traffic straight up to the production database on floor 4?
Yes.
That feels like an enormous security flaw to bake into the default configuration.
It definitely sounds like a flaw today, but it is actually a legacy of how Kubernetes was originally conceived. You see, Kubernetes was heavily influenced by Google's internal container orchestrator, Borg.
Oh, right, Borg.
Yeah, and the primary design goal back then was reducing friction for developers building highly distributed microservices. They wanted networking to be out of the way, really prioritizing speed and collaboration over zero-trust security.
So they built the floors to keep the desks organized, but they left all the internal air vents wide open.
That is the perfect way to visualize it, yes. Namespaces provide organizational isolation. They do not provide network isolation.
Okay, that makes sense.
If you want to block those air vents and enforce strict traffic rules between floors, you have to explicitly define and apply network policy objects, which basically act as internal firewalls. Relying on namespaces for network security is just a fatal error.
That distinction is paramount. Okay, so we understand the structure of our environment, and we know how to navigate the network topology. Let's pull this back to our initial problem configuration management.
Right, the hard-coded password.
Exactly. If we have a back-end application that needs to run in the staging namespace and then move up to the production namespace, how do we handle its configuration without hard-coding data into the image?
Well, the foundational rule of container orchestration is that your container images must be immutable. You build the image once, but the environment that image runs in changes constantly.
Right, the database URL in staging is going to be totally different from the database URL in production.
Exactly. So to solve this friction, Kubernetes extracts the configuration data away from the pod and stores it in an object called a ConfigMap.
So if namespaces are our floors, ConfigMaps are kind of like the whiteboards mounted on the wall of each floor.
I like that.
Yeah, like the production floor has a whiteboard that says connect to the prod DB. The staging floor has one that says connect to the staging DB. The application code is identical, but when the pod boots up, it reads the local whiteboard to orient itself.
Precise.
But wait, if I have like 100 microservices on a floor, I'm not writing 100 config maps by hand in the terminal. How does this actually scale in the real world?
Oh, in reality, you aren't doing it manually at all. You manage config maps declaratively using deployment tools like Helm or Customize. You feed your configuration files into these tools, and they automatically generate the config map manifests during your CI/CD pipeline.
Oh, okay, that makes more sense.
But the real operational complexity comes when you decide how to mount that config map into your pod. You generally have two choices. You can inject them as static environment variables or mount them as files within the pod's file system.
Now, assuming you, the listener, already understand what an environment variable is, let's talk about the operational friction there. Because setting an environment variable in a deployment manifest is pretty trivial. But there's a catch regarding how static they are, isn't there?
There is a severe limitation, actually. Environment variables are injected exactly once during the container initialization process. I once consulted for a team that experienced a massive cascading outage because they didn't fully grasp this.
Oh, no. Let me guess. They updated a config map with a new database IP address?
Yep. And the deployment used environment variables. So the running pods completely ignored the update. They continued using the old stale IP address for 3 weeks.
3 weeks. Wait, so what happened? A node went down, the pods got rescheduled, and suddenly they booted up, pulled the new IP address, but the database migration hadn't been completed yet.
Close. The legacy database was finally decommissioned, and instantly, every pod that was still relying on the stale environment variable just crashed.
Ouch.
Yeah, they assumed that updating the config map would automatically update the applications. If you want dynamic updates, you have to mount the config map as a volume.
See, here's where it gets really interesting to me. How does the system update a file inside a running isolated container without crashing the application process that's currently reading it?
It relies on a highly sophisticated kubelet sync loop. When you mount a config map as a file, the kubelet periodically polls the API server for changes. When an update occurs, the kubelet doesn't just overwrite the active file, because that could cause a read error for the application. Instead, it writes the new data into a hidden timestamp directory on the host.
Oh, clever.
Right. Then atomically updates a symbolic link, a symlink, inside the container to point to that new hidden directory.
So the application is basically just reading a shortcut, and Kubernetes is quietly swapping out the destination of that shortcut in milliseconds.
Yes. The swap is instantaneous. If your application code is written to watch its configuration files for changes a pattern known as hot reloading, it will instantly detect the symlink update and adjust its internal behavior without ever dropping a connection or requiring a pod restart.
That is just an incredible piece of engineering. So, okay, config maps are perfect for dynamic, non-sensitive data. But going back to our developer's $50,000 nightmare, you cannot write your master database password on a whiteboard in the middle of the office floor.
No, you definitely cannot.
That brings us to secrets.
Right. Kubernetes provides the secret object specifically to handle sensitive credentials. So API tokens, SSH keys, TLS certificates, passwords. Like config maps, they are namespace scoped.
So they are the locked filing cabinets on the floor?
Conceptually, yes.
No.
But we need to address the most dangerous misconception in the entire Kubernetes ecosystem.
Let's hear it.
Well, this raises an important question. When you create a secret in Kubernetes, the system automatically applies base64 encoding. Many developers see that scrambled string of text and just assume their data is now secure.
Wait, hold on. If it's just base64 encoded, the name secret is completely misleading. Base64 isn't encryption at all.
It absolutely is not. Base64 is an encoding scheme designed for data transport, not data security. Let's look at the actual mathematics of how it works for a second.
Okay.
Base64 takes raw binary data, groups it into 24-bit blocks, and then divides those blocks into 4 6-bit chunks.
Right, breaking it down.
Exactly. And since 6 bits can represent exactly 64 different values, it maps each chunk to a standard, universally readable ASCII alphabet. So uppercase and lowercase letters, numbers, a plus sign, and a slash.
So it's essentially just physically repacking boxes of data into standardized shipping containers, right? Just so they don't get corrupted when traveling between different computer systems.
That's a great analogy.
There is no randomized cryptographic key involved. There is no complex algorithm locking the data.
None whatsoever. Anyone with access to that secret can run a single base64 decode command in their terminal, and the system just reverses the mathematical mapping, instantly revealing your production password in plain text.
That's terrifying.
It is. Confusing data formatting with cryptographic encryption is the #1 reason organizations fail security audits. And by the way, it is heavily tested on the KCNA.
Wow, that completely shatters the locked filing cabinet metaphor. I mean, the cabinet isn't locked at all. It's just got a sign on it written in a universally understood code, which leads to an even more terrifying realization about how the cluster stores this data long term. Let's talk about et cetera.
Right. Et cetera is the highly available key value store that serves as the ultimate brain of your Kubernetes cluster.
Yeah.
Every single piece of state, every deployment, every namespace, every config map, and every secret is permanently stored in the et cetera database.
And because base64 is just formatting, that means by default, Kubernetes takes your highly sensitive database password and writes it directly into the cluster's hard drive in plain text.
That is the uncomfortable truth of default Kubernetes architecture.
So what does this all mean for someone taking an exam versus someone building a real production environment? Because there is a massive paradox here. If a test asks me which object stores sensitive data, the textbook answer is secret. But practically speaking, it's not actually secret.
It is the difference between intent and implementation. The secret object establishes intent. It signals to the orchestrator and to other engineers that this specific piece of data requires careful handling.
Okay, I see.
For instance, the system is hard-coded to never output the contents of a secret object into standard terminal logs. But the implementation of actual cryptographic security is left entirely up to the cluster administrator.
So how do we actually secure it? We can't just leave plain text credentials sitting in etc., waiting for an attacker to compromise the control plane.
The baseline industry standard is enabling encryption at rest. This requires configuring the Kubernetes API server with an encryption configuration resource, which hooks into a key management service provider.
Right.
Before the API server writes your secret to etc., it actively scrambles the data using a real cryptographic key. So even if an attacker steals the raw etc. database files, all they get is mathematical gibberish.
But even then, the password still exists inside the cluster. I know a lot of enterprise environments prefer to never let Kubernetes handle the actual credentials at all.
Which is the more advanced and honestly increasingly standard approach. Organizations use dedicated external vaults like HashiCorp Vault, AWS Secrets Manager, or Azure Key Vault. They keep the credentials entirely outside the cluster.
But the pod still needs the password to connect to the database. How does the pod get it if Kubernetes doesn't have it?
You implement an external secrets operator or use a container storage interface, a CSI driver. When a pod spins up, a specialized sidecar container or the underlying driver basically intercepts the process.
Okay.
It authenticates directly against the external vault, securely retrieves the credential over the network, and injects it straight into the pod's in-memory file system.
Bypassing etc. entirely. The system never writes it to the hard drive. That is brilliant.
It is the only way to achieve a true zero-trust posture regarding configuration data. You use the native tools for orchestration, but you delegate the cryptography to purpose-built security systems.
All right, let's pull all of these mechanisms together for a final wrap-up. If you want to survive the real world and ace your certifications, you need to master 3 fundamental environmental controls. First, namespaces. These provide structural multi-tenancy and resource quota enforcement to prevent noisy neighbors. But remember, the network is completely flat by default. Namespaces are organizational barriers, not internal firewalls.
Right, and you must use network policies to restrict cross-floor communication.
Second, ConfigMaps. They abstract non-sensitive configuration data away from your immutable container images. And if you want zero downtime hot reloading, avoid static environment variables. Mount them as volumes so the kubelet sync loop can atomically update the symlinks.
Correct.
And third, secrets. They are meant for sensitive data, but remember the absolute golden rule, base64 encoding is data formatting, not encryption. It mathematically translates data, it does not lock it. You must configure encryption at rest in your control plane, or utilize external operators to keep plain text data out of your etc. database.
Perfect summary. And, if we connect this to the bigger picture, you have to look at the historical context of container orchestration. Kubernetes was built to enable velocity. The open network model, the unencrypted storage of state, and etc. These were deliberate choices made to reduce friction and help teams deploy distributed systems faster.
Makes sense.
Security was treated as an overlay, an opt-in feature that you have to actively design and implement.
It prioritized getting the system communicating over keeping the system locked down.
Precisely. So I want to leave you with this final thought.
Yeah.
We spent a massive amount of engineering effort securing the perimeter of our clusters, writing complex RBAC rules, and scanning container images. But consider the underlying physical or virtual infrastructure that your control plane runs on. If an advanced persistent threat manages to bypass your API server entirely and gains direct access to the raw disk storage of the virtual machine running, etc., every single configuration, every service account token, and every secret is exposed. How much of your entire organizational security relies purely on the assumption that the hypervisor layer itself will never be breached?
Wow, that is a terrifying and phenomenal question to chew on. And it's exactly why mastering the mechanisms of your environment is just as vital as mastering your application code. Thank you so much for joining us on this deep dive. Take these tools, secure your systems, and please never hard code a password again. We'll catch you on the next one.